Okay, now in part D, the question is, how does K affect the system's ability to reject W? And you notice that really this didn't matter. In part C, the result didn't matter. It happened for all values of K. So part D is pretty easy in this case. For all K greater than 0. That's our underlying assumption in this class. K is greater than 0. Then y of infinity, due to the disturbance, goes to 0. Okay, so that's part D. Next, we're looking at part E. We want the characteristic equation of the system. All right, so looking back at our system, we know that we have a D, we have a G. And to get the characteristic equation, we simply need to look at the closed loop transfer function, assuming that W is set to 0. Okay, so in the closed loop transfer function, this would be D times G over 1 plus D times G. Okay, and so when we plug in, we know that D is S plus 1 over S, and G is 3 over S plus 2. And then on the bottom we have 1 plus K S plus 1 over S, 3 over S plus 2. And we want to look at the denominator. The denominator polynomial is where you find the characteristic equation. So we need to do a little bit of algebra. We notice that we need a common denominator. So we can multiply top and bottom by S plus 2. So this applies across the numerator and the denominator. Okay, and when that happens, I get that the transfer function is given by, notice these cancel, and we get K S plus 1 times 3, and in the denominator S plus 2 plus K S plus 1 times 3. So our characteristic equation is found by looking at the denominator. So the characteristic equation is S times S plus 2 plus K S plus 1 times 3 is equal to 0. So that's the answer for part E. Then for part F, what I want to do for part F is sketch the root locus. Okay, so for the root locus, we need to know what L of S would be, and we can get that from the characteristic equation because we have this set up. When we developed root locus theory, we knew that this was A of S, and this is B of S, and L, K times L of S, is going to be B of S over A of S. Well, let's write A of S, which in this case is 3 K S plus 1 over S plus 2. So the K's divide out, and we get that L of S is S plus 1 times 3 over S plus 2. Okay? All right, so that leads us to part F. In part F, we are looking to do the root locus for L of S. Okay, so to do the root locus, we need to put the poles and zeros down. And so we see here at -1, we have a 0. At the origin, we have a pole, and at -2, we have another pole. So there's our poles. And then we know we have 2 branches, and we can calculate phi, n is equal to 2, m is equal to 1, so phi is equal to 180. All right, so we know that at least one of the poles is going to go to negative infinity along the real axis. All right, and from there we're ready to do the root locus. We know that the real part in here is on the root locus, and that the real part of the real axis is on the root locus in this region as well. Okay, so this pole moves towards that 0, and this pole moves towards the 0 at infinity. That satisfies all the rules that we've talked about for the root locus. So that's what I would expect to see on an exam for a problem like this. All right, but I also want you to be able to answer questions about the system. And so you see, with this root locus, we can conclude that no matter what k would be, for all values of k bigger than 0. At 0 we had a problem because we had that pole right here at the origin at k equals 0, because essentially it was an open loop system, and then so k equals 0 is not an interesting case. So for all of the values of k bigger than 0, all the poles are left hat plane, which implies BIBO stable.